Hello, my name's Andrew Christlieb. I'm a University Foundation Professor at Michigan State University, and I'm also the Director for the Center for Hierarchical and Robust Modeling of Non-Equilibrium Transport. The mission of CharmNet is to create the tools that we need to use in computer software to be able to do active design and control of non-equilibrium plasma, specifically fusion energy. Many models in physics are a reduction or an abstraction or a simplification. The first principles model tries to include all of the fundamental dynamics that happens in the real system. First principles is trying to capture the impact of physics related to those very fine scale interactions. It's not reduced. Many fusion systems are in a non-equilibrium state. We mean that the system is doing a dynamic compression or it's doing a dynamic transition. In a lot of these systems, it's sufficiently complex that we can't really do first principles the way we want. The goal when we talk about modeling these systems with first principles is to build tools that can capture effects that have been heretofore beyond what we could possibly do. Often what we will do is use data from the experiment as a surrogate to augment the model and make the model better. And in this context, it's often through a machine learning process where you train the model on things you know how to simulate, and then you use the experiment to do something called transference learning. It's a way of actually directly incorporating the experimental data into the surrogate you're building, the machine learning surrogate. And in doing so, you build in physics from the experiment that you weren't able to capture through your simulation. That's a total game changer. That means these high dimensional problems we're trying to do now suddenly become something we can solve. So up till now, we've been using reduced models to do the design of these things, and they're not accurate enough at capturing the fundamental effects. So we're really trying to create the infrastructure that the engineer can then take and go run and do a bunch of iterations on design to understand what the right configuration is for the system they're interested in. Multi-scale modeling is really the science/art of trying to build models that incorporate small-scale physics in coarser models that we can actually simulate with. We're trying to bridge this huge range of coupled scales where the physics at the smallest scale can create instabilities that impact the largest scale. So if we're thinking about the differences between a kinetic model and a fluid model and being able to simulate these systems, a fluid model is the observables, right? We can measure mass, we can measure momentum, we can measure energy. In a kinetic model, you're actually stepping into the world of every particle has its own energy, every particle has its own velocity. Kinetic model has these very fine scale effects, but those fine scale effects can lead to all sorts of important instabilities in plasmas, which is why we need to know about them. And the fluid model, well, it's what we can simulate easily. In a perfect world, we would have a fluid model, which is our bulk description, that captures kinetic effects, but that's some perfect fantasy world. And we're trying to get there by making machine learning surrogates that fit into the fluid model in some way that allows us to capture those effects. Most important lesson I've learned as a researcher is just be open to new ideas. Don't ever be so committed to an idea you're studying to not really hear that the person talking to you might be explaining to you a completely new way to do something that might completely change your perspective.